Middle distillate products derived from tight oil can experience problems with cold flow properties such as pour point, water separation, and lubricity. Some of the light ends produced when running shale crudes may experience copper strip problems. Gasoline octane suffers due to the paraffinic nature of these crudes, with FCC gasoline octane on average 8 to 10 numbers lower when running tight oil-derived feeds compared to conventional vacuum gas oil. Finally, blending the residual materials from shale oil with asphaltenic stocks can reduce fuel oil stability. The following table compares the properties of middle distillates, diesel and kerosene, of the tight oils Bakken and Eagle Ford versus paraffinic crudes. For refineries that are designed with higher hydrogen partial pressures and lower space velocities, the upgrading of tight oil can increase the production of liquefied petroleum gas or LPG and fuel gas if the production fields where the tight oil is being produced recovers light ends and retains them within the crude. The added strain from the higher amount of LPG produced from tight crudes on the crude tower LPG recovery system could result in operability and reliability issues. Because the increase in both LPG and fuel gas production can result in the existing saturates gas plant to be overloaded, the refiner may need to debottleneck the gas plant. Options to debottleneck the gas plant include the addition of packing and/or high-capacity trays to existing columns and the addition of new columns within the gas plant. Due to the low sulfur content and paraffinic nature of typical tight oils, the quality of refined products can suffer when processing these crudes. This table shows the research octane number and octane rating of gasoline and the API gravity, aniline point, and diesel index of light cycle oil distilled from whole Bakken crude. These light, high API feeds have been shown to have a lower residuum cut. For example, in the U.S., Eagle Ford only has a 1.6 weight% of resid, and the resid cut of Bakken is only 4.55 weight%. In comparison, WTI has 6 weight% resid, Brent has 9 to 11 weight% resid, and Maya has 37 weight% resid. Less residuum means less material for bottom-of-the-barrel upgrading units, such as cokers. At a past American Fuel and Petrochemical Manufacturers Q&A and Technology Forum, it was mentioned that U.S. Gulf Coast refiners who had previously upgraded coking units would not have enough material to operate these units. Representatives from Flint Hills Resources and AMEC Foster Wheeler stated that outside purchases of heavy fuel oil or vacuum resid may be necessary to fill cokers at refineries processing large amounts of tight oil. Flint Hills Resources also mentioned that they recycled heavy coker gas oil to the heater for a short period of time. FCC slurry can also be added to the feed at about 10% capacity. When processing large amounts of LTO, the lack of residuum may actually make coker units unnecessary. This table summarizes the problems with some refined products when processing tight oil. Light ends from tight oil can cause copper strip corrosion, while tight oil naphtha can cause corrosion and water shedding. Both jet fuel and diesel from tight oil can cause conductivity, lubricity, stability, and water shedding. Fuel oil from tight oil has been shown to cause asphaltene instability and gum deposits. Naphtha derived from tight oil is predominantly paraffinic, which results in a lower N+2A or volume of naphthanes plus twice the volume of the aromatics content. The lower N+2A content means that at the same severity, processing naphtha derived from tight oil in a reformer will reduce C5+ and hydrogen yields while at the same time increasing fuel gas and liquefied petroleum gas yields from the reformer. The uptick in fuel gas and liquefied petroleum gas yields from processing naphtha from tight oil in a reformer can be challenging, and this is why alkylation has been preferred for producing a high-octane gasoline blend stock when processing tight oil in a refinery.